First of all, I would request all my listeners to like, subscribe, and share my channel. My lectures may not be used in any way for any business purposes. Today we are going to study interference, diffraction, and standing waves. Table of contents, principle of superposition, constructive and destructive interference, path difference and phase difference, interference patterns, diffraction, examples of interference and diffraction, study of intensity curves, diffraction grating, using different light sources, Young's double slit experiment, dispersion of white light using diffraction grating, intensity distribution curves, standing waves, modes of vibrations when both ends are closed, resonance, standing waves in an open pipe, fundamental and harmonics, and end correction. Principle of superposition. According to the principle of superposition, when two or more than two waves pass through a region in space at the same time, the net displacement is equal to the algebraic or the vector sum of the individual displacements. So these two waves, red and green, their superposition will give rise to this resultant, this purple color. Considering 2-3 points here, like for example, at this point, green and red both have the same displacement, 3. Their algebraic sum give rise to 3 plus 3 equal to 6. At this point, green has minus 2.7 and red has minus 4. Minus sign indicates that these points lie along minus y-axis. Their resultant gives the algebraic sum minus 2.7 plus minus 4 minus 6.7, this one. Again, this point is at minus 0.9 and this one minus 2.1. Their algebraic sum gives minus 3, so resultant is this one. Now these two diagrams show constructive and destructive interference. Waves that combine in phase add up to give bright fringes. This is called constructive interference and sources are said to be coherent. In this case, see, this crest overlaps with crest. So path difference is 0. So constructive interference will take place and we will get bright spot. Here in this case, crest lies over trough. So destructive interference will take place and we will get dark band or dark spot. Waves that combine 180 degree out of phase. These two are 180 degree out of phase or lambda by 2 path difference. So when waves combine 180 degree out of phase, they cancel out each other and yield dark fringes. They are coherent still as the sources have a constant phase difference, the same frequency and the same waveform. Again, I have drawn this sketch for showing the constructive and destructive interference at different points from two coherent sources, of the waveforms from two coherent sources. For constructive interference, path difference is an integral multiple of wavelength, and for destructive interference, path difference is an odd multiple of wavelength. Now these dark lines show crests and lighter or thin lines show troughs. And it can be seen that when path difference is 0, like here at this point, these all red points, wherever they lie, it can be seen that their path difference between two wavefronts, it is 0. So we will get bright bands here. This is central maximum, m is equal to 0. This is first order, second order. On both sides we will get maxima and minima. Minima lies on these lines, blue points. So this crest and this crest, so path difference is 0. Here trough from one wave and trough from another wave, they overlap, again path difference is 0. So it will be constructive interference all over there, here, all red lines. And in this case, see this blue point, one crest and one trough overlap each other. So they will interfere destructively because path difference here is lambda by 2. See, path difference between one crest and one trough is lambda by 2, and path difference between consecutive crests or between two consecutive troughs is 1 lambda. Again, this shows interference pattern, bright and dark fringes. So interference effects are observed with all types of waves like light, radio, acoustic, water, gravity, and matter waves. Now, how to differentiate between path difference and phase difference? Path difference is the extra distance traveled by one of the waves compared with the other. So in these two sinusoidal waves, the path difference is lambda by 4. And phase difference between these two waves is pi minus pi by 2, pi by 2, which is 90 degree, because pi is 180 degree. Now here we observe interference pattern. There are different types of experimental setup to view or observe interference fringes. For example, this is another experimental setup, Michelson interferometer. Newton rings are also examples of interference fringes, but here you may see that only experimental arrangement is different. Now, diffraction. Bending of waves around obstacles and spreading out when traveling through small slits or aperture is called diffraction. See these incoming wave fronts. When they pass through a hole in the wall or any aperture or opening, they bend around the edges. This diffraction pattern. Direction changes of waves as they pass through hole. These blue lines are crests, wave crest, and in between blue lines there are wave troughs. The most important point here to note is that for diffraction to take place, size of the slit should be comparable with the wavelength of incident wave. This size of slit should be comparable with the wavelength of the incident wave. Diffraction occurs with all kinds of waves, including sound waves, water waves, and electromagnetic waves, such as visible light, X-rays, and radio waves. All physical objects have wave-like properties. Diffraction of matter also occurs and is studied using the principle of quantum mechanics. The expanding profile of a laser beam, the beam shape of a radar antenna, and the field of view of an ultrasonic transducer are analyzed using diffraction equations. Now here you can compare two kinds of diffraction, not two kinds of diffraction, actually here large opening, so diffraction is not good, right? Because wavelength of incident light and width of the opening are not comparable to each other. Width of opening is much larger, so very little diffraction takes place. Here it is comparable with the wavelength of the incident light, so this diffraction is far better than this. Now examples of interference and diffraction. These soap bubbles, they are example of interference. These CDs and DVDs. The closely spaced tracks on a CD or DVD act as a diffraction grating to form the striking pattern seen when looking at the disc. Same here. These glorious colors do not come from pigments in the wings but arise as a result of scattering of light waves from different points on the wing and meet in our eyes and combine to give rise to interference. So this is how diffraction takes place. Incident light is white light source passing through diffraction grating. We will study it in detail in the next slides and see how the spectrum is produced on both sides of the principal maxima. This center is white because all waves merge here. All wavelengths are together here and wave path difference is 0. But on each side we get principal maxima of each wavelength because each wavelength is deviated through a different angle. The intensity pattern in double slit. This sunlight, light coming from sun, passing through a single slit. After that, it passes through two slits, S1 and S2. Distance between two slits is D. and after that we get interference pattern. Bright fringes are all equally bright. It can be seen here that bright fringes are all equally bright if slit widths are of negligible size. These slit widths are of negligible size, so we get the same intensity everywhere. Central fringe, known as central maxima, here this white color, 0, will be white as path difference is 0 and all overlap there, as I have told earlier. Now these are comparison of intensity distribution due to single and multiple slits. So due to single slit, we get this pattern. Due to double slit, this pattern. Due to 3 slits, this one. And for 5 slits, this one. So it can be seen here that maxima, they are of rapidly falling intensity here, right? Due to diffraction, and they are well defined as number of slits increase as compared to when it is due to single slit. Now what is a diffraction grating? It's a polished surface, usually glass or metal, having a large number of very fine parallel grooves or slits and used to produce optical spectra by diffraction of light or transmitted light. Diffraction gratings are used in monochromators, spectrometers, lasers, wavelength division, multiplexing devices, and many other optical instruments. These are used as sensor of fluid property due to the sensitivity to the refractive index of the media. See this diffraction grating. Monochromatic light of laser light. See, monochromatic means having one wavelength, one color. Here, I would like to mention that in case we use laser in experiments, care must be taken to follow correct safety procedures. One should wear eye protection and avoid following the beam to enter eye directly. This is screen, this diffraction grating. So it can be seen here that after passing through the diffraction grating, each wave travels different distance. And in order to calculate how much is the path difference between any two waves, we have to use this way. Like it can be seen that this wave travels the shorter distance, this one little longer again, and this is the longest. So in order to calculate the path difference, say this angle is theta, which these rays make with the horizontal line. If this angle is theta, this angle is also theta, because according to a rule in mathematics, angle between two lines is equal to angle between their perpendiculars. This line is perpendicular to this horizontal line, this line is perpendicular to this line, so this angle is theta, and this path difference, the difference in path which two waves have, it is equal to d sine theta. Young's double slit experiment. This experiment was developed by physicist Thomas Young to demonstrate interference of light waves. See here again path difference, d sine theta, where d is the distance between two slits. Waves spreading out from narrow slits, an interference pattern consisting of alternating constructive and destructive interference is observed. So this path difference d sine theta will be equal to m lambda, where m is an integer 0, 1, 2, 3 and so on, and we will get bright fringes in this case. When path difference is m plus half lambda, we get dark fringes. Now these are effect of interference and diffraction by using different light sources. Say in this case laser light is used. Here we use sunlight and make the source coherent by passing through a single slit and then in two slits. This is light bulb. So you can see different kinds of pattern. Basic principles are same, but you can see that how these fringes lie. Diffraction grating. Again, after passing through different slits. Each we get central maxima white color and first order maxima on both sides of it, then second order maxima, and you can see that this kind of dispersion takes place of white light into 7 colors: violet, indigo, blue, green, yellow, orange and red. So if we shine white light onto a grating, we produce a series of spectra each side of the central fringe. This is because white light is made of many frequencies which all diffract at slightly different angles. Now, dispersion of white light using diffraction grating. Sun or any other source of white light viewed through a diffraction grating gives the following result. Rainbow dispersion pattern on either side of n equal to 0, as we have studied already. Central maxima is white as all overlap there. This also we have studied before. And higher order maxima can overlap. You can see when we go to higher orders like m equal to 2, m equal to 3, their central maxima overlap here, this point and this point. Now, intensity distribution. Intensity maxima are brighter and sharper than in two slit case, as we can see here. So, intensity distribution for two colors, equal mixture of red and blue when we use equal mixture. The longer wavelength red light is diffracted more than the shorter blue wavelengths. As red light has longer wavelength, it is diffracted more. So these are all first order maxima, second order maxima on both sides for blue color, and this first order maxima, second order maxima for red color on both sides. Now, standing waves. First noticed by Faraday on the surface of a liquid in a vibrating container. Meldy demonstrated this phenomena with vibrating strings. Stationary or standing waves are waves with boundary conditions. They oscillate in time, but peak amplitude profile does not move in space. Oscillations at different points throughout the wave are in phase. Nodes have zero amplitude or minimum amplitude, and antinodes have maximum amplitude. See these points, nodes, where amplitude is 0. This one, this one, this one, here. Similarly here, these are nodes, all where amplitude is 0, this one. And where amplitude is maximum, these are antinodes. This is the resultant waveform of the standing wave. And these two are waves which give rise to this resultant. Now we can see, there are 5 cases. When t is equal to 0, when t is equal to 1 by 4t, this capital T denotes time period, time taken to complete one vibration. Then this third case is when t is equal to half of time period, t is equal to 3 by 4 of time period, and when t is equal to capital T. Now first we will see here when at t equal to 0, this first case, the progressive waves traveling to the left and right are in phase. Waves are in phase, hence constructive interference takes place. Now second case, this one, at t equal to t by 4, waves are 180 degree out of phase. You can see this crest lies over trough. They are anti-phase, out of phase, 180 degree out of phase. Hence, interference is destructive. Now, in third case again, waves are back in phase again, so constructive interference will take place. Case number 4, when t is equal to t 3 by 4t, waves are out of phase again and destructive interference takes place. And last case is again when t is equal to capital T, again in phase, so constructive interference will take place. It can be noted that separation between adjacent nodes here or anywhere along these 5 cases, separation between adjacent node is lambda by 2, where lambda is the wavelength of sound or any wave, and nodes and antinodes are separated by lambda by 4. See this node anywhere, antinode and node, lambda by 4. Also, speed of the progressive wave is equal to v, which can be found by the equation v equal to f lambda, where f is the frequency of the waves. And it can be noted that in case of these stationary or standing waves, wave velocity is 0 as it does not travel and does not transfer energy. Now see how these waves are formed, stationary waves. When the string of a musical instrument like guitar is plucked halfway along its length, when both ends are fixed, it vibrates with an antinode at its midpoint. Here, this is midpoint, antinode. This is known as fundamental mode of vibration of string. The fundamental frequency of a standing wave is the minimum frequency for a given system or arrangement. So these are some of the possible stationary waves for a fixed length of string of length L. The frequency of the harmonic is a multiple of the fundamental frequency, as can be seen. Twice, 3 times. A guitar string may vibrate with 2 antinodes. See here, along its length. This gives a note having twice the frequency of the fundamental and is described as a harmonic of the fundamental. Harmonic frequency is always a multiple of the fundamental. Resonance. Resonance is a phenomena in which an oscillating or vibrating system is made to oscillate at a frequency which is the same as its own natural frequency. The system vibrates with increasing amplitude and a loud voice or note is heard. Here, when a vibrating tuning fork, this is a tuning fork, when it is held above the open end of a cylindrical air column which is closed at the other end, longitudinal waves are sent down the air column. These waves are reflected at the water surface and thus produce standing waves. Nodes are produced at the water surface and antinodes are produced at the open end. When the frequency of these waves in the air column becomes equal to the natural frequency of tuning fork, a loud sound is produced in the air column. It is the condition for resonance. It occurs only when the length of air column is proportional to 1/4 of the wavelength of sound waves having frequency equal to frequency of tuning fork. So for first resonance, this length L1 should be equal to lambda by 4, and for second resonance it should be equal to 3 lambda by 4. So this is position of second resonance, this is position of first resonance. Now standing waves in an open pipe. Now as I have already mentioned that a musical instrument has a set of natural frequencies at which it vibrates at when a disturbance is introduced into it. These natural frequencies are known as the harmonics of the instrument. Each harmonic is associated with a standing wave pattern. Now what is a standing wave pattern? It is a pattern, a vibrational pattern created within a medium when the vibrational frequency of the source causes reflected waves from one end of the medium to interfere with incident waves from the source in such a manner that specific points along the medium appear to be standing still. In the case of stringed instruments, standing wave patterns were drawn to depict the amount of movement of the string at various locations along its length. Such patterns show nodes at the two fixed ends of the string. In the case of air columns, a closed end in a column of air is analogous to the fixed end on a vibrating string. That is, at the closed end of an air column, air is not free to undergo movement and thus is forced into assuming the nodal position of the standing wave patterns. On the other hand, air is free to undergo its back and forth longitudinal motion at the open end of an air column, and as such the standing wave patterns will depict antinodes at the open ends of air columns. Therefore, the standing wave patterns for air columns show vibrational antinodes at any open end. Here see, there are two antinodes and one node, and vibrational nodes is at any closed end. If this principle is applied to open end air column, then the pattern for the fundamental frequency, which is the lowest frequency and longest wavelength pattern, will have antinodes at the two open ends and a single node between them. This first case. This is second harmonic and this is third harmonic. The standing wave pattern for the fundamental frequency for an open end air column looks like this first diagram. Now the distance between antinodes on a standing wave pattern is equivalent to 1/2 of the wavelength. It can be seen here that this length is equal to λ/2. Adjacent antinodes are positioned at the two ends of the air column. The length of the air column is equal to 1/2 of the wavelength for the first harmonic. Now the standing wave pattern for the second harmonic. See this second diagram of an open air column. It has how many nodes and antinodes? 3 antinodes and 2 nodes. There is one full wave in the length of the air column. That is twice the number of waves that were present in the first harmonic. Therefore, the frequency of the second harmonic is twice the frequency of the first. It can be calculated in this way as well. By substituting the value of lambda, we can get the second harmonic is twice the frequency of the first harmonic. The standing wave pattern for the third harmonic. See this third diagram of an open end air column has how many antinodes and nodes? There are 4 antinodes and 3 nodes. So there are how many waves? There are 1 and 1.5 waves present in the length of the air column. 1 and 1/2 waves is 3 times the number of waves that were present in the first harmonic. Hence, the frequency of the third harmonic is 3 times the frequency of the first harmonic. Now this is again just a recap of the previous slides, fundamental and harmonics, in case of when one end is closed and one end is open, and in both open ends. End correction. End correction is an example of a systematic error. The antinode at the top of the tube is shown extending slightly beyond the open end of the tube. The air slightly beyond the end of the tube vibrates as part of the stationary waves. So how to apply this end correction for eliminating errors? You may see that L1 is equal to λ/4, L2 is equal to 3 λ/4. Now, as I have told that in acoustics, end correction is a short distance applied or added to the actual length of a resonance pipe in order to calculate the precise resonant frequency of the pipe. So this way I will show you how we eliminate errors by applying this end correction. So from the diagram it is clear that in case of the first resonance position, L1 plus E will be equal to λ/4. So we have to take into account this part E. Label it as number 1. In second case, L2 plus E is equal to 3 λ/4. Now by subtracting 1 from 2, we get 3 λ/4 minus λ/4 equal to L2 plus E minus L1 plus E. By simplifying, we get 2 λ/4 equal to L2 minus L1, or λ/2 is equal to L2 minus L1, or lambda is equal to 2 L2 minus L1.